Welcome to Visual Algebra Lecture 4.3, the Fundamental Homomorphism Theorem. The isomorphism theorems describe the relationship of groups, their subgroups, and quotients. Some books number these, and others give them names, which is what we will do. The first isomorphism theorem will be called the Fundamental Homomorphism Theorem, and it says that the quotient of a group by its kernel is isomorphic to the image. In other words, every homomorphic image is a quotient. In this lecture, we will prove this theorem and then see some basic consequences of it. We will explore it using Cayley graphs and Cayley tables. And finally, we will see how every homomorphism can be decomposed into the composition of a quotient followed by an embedding. Okay, let's get started. The Fundamental Homomorphism Theorem, or FHT for short, is one of the central results in group theory. It says that if phi is a homomorphism from G to H, then G mod the kernel of phi is isomorphic to the image. This says that every homomorphism can be decomposed into two steps. First, quotient G out by the kernel to get a group of cosets, and then relabel those cosets via an isomorphism. It helps to see an example, and this one should be familiar because we saw it in the previous lecture and even back in chapter 3 when we first learned about the quotient process. Phi here is a homomorphism from the quaternion group to the Klein 4 group, defined by sending I to V and J to H. Remember, we proved in the previous lecture that the preimages of the elements in the image are the cosets of the kernel. So this is the kernel, and here are the other cosets. The Fundamental Homomorphism Theorem says that this homomorphism can be done in a two-step process. First, we can take the quotient by the kernel, that is, collapse these cosets into single nodes. Notice that the result of this is a group of cosets, but it is isomorphic to V4, which is the image. So that means that there is a natural isomorphism or relabeling of nodes or cosets down here with elements up here. Do you see how to define that? Starting with n. Well, we take the preimage of that up here, and then where does that get mapped? And that tells us that n gets sent to there. What about the coset in? Say, okay, where did that come from? Take the preimage. Where does that go? And that tells us that in goes up here, and so forth. Jn goes here, and kn goes here. We will formalize this shortly. Here is another way, this time in terms of Cayley tables, to think about the homomorphism that we just saw on the previous slide from Q8 to V4 as the composition of first a quotient by the kernel and then an isomorphism or relabeling map to the image. Remember, as early as chapter 1, I've introduced you to the concept of a quotient as what you get when you take a Cayley table and you rearrange the elements in a certain way and squint your eyes and you see the Cayley table of a smaller group. And this is the example that I started you with. This is Q8, and if you arrange the elements or cluster them in this way, you see a copy of V4 like this. Now, previously I just colored in this way and you squinted your eyes and you saw it, but now I can tell you that these squares are actually cosets. So the elements in the green squares are the elements in N, the elements in the red squares are the elements in the coset In, and so forth. So this group of cosets has a structure of V4, which means that there's a natural labeling map from these elements to E, V, H, and R. And you see how that's defined? So where does In get sent? I'll go up here. Where does I get sent? It gets sent to V. Jn, well, J gets sent to H, so I'll send Jn, this coset, to H, and so forth. Okay, now it's time to prove the Fundamental Homomorphism Theorem, that if phi is a homomorphism from G to H, then the image of phi is isomorphic to G mod the kernel of phi. We will do this by constructing an explicit map between these two groups and proving that it's an isomorphism. Let's denote the kernel of phi by n for short, and recall that G mod n, by definition, is the set of cosets of n. Remember, since n is normal, it doesn't matter if we use right cosets or left cosets. They're the same thing. I've already explained in the previous 2 slides how that map should be defined, so the only challenge here is writing that down formally. So let's take a coset in the domain, call it Gn, and which element in the image should we send that to? Well, we don't really have any choices. Well, we have G as a representative in this coset, so let's just pick phi of G. First, we have to show that iota, the map that we just wrote up here, is actually well-defined, meaning it does not depend on our choice of coset representative. In other words, if we have 2 different ways to write the same coset, say an and bn are the same, then will this definition better send these 2 things to the same place? Otherwise, it's not actually a function on the set of elements. We'll come back to this concept of well-definedness later in this lecture because it's not the first time we've seen it. Recall that we encountered it in a different context when we first learned about quotient groups. But right now, let's prove this implication. So suppose we have 2 different ways to write the same coset. That's an equals bn. Well, we can left multiply by b inverse and write that as b inverse an equals n. Recall that by our so-called boring but useful coset lemma, that this means that b inverse a is actually in the subgroup n. Since n is the kernel by definition, that means that phi of b inverse a is the identity element in H. Now we can apply basic properties of homomorphisms and write this as phi of b inverse times phi of a equals the identity. And we can move this to the right-hand side and write this is phi of a equals phi of b. And recall that's the definition of iota. So that means that iota of an equals iota of bn. So indeed, if we started with the same coset written 2 different ways, our definition sent those the same place. So iota is well-defined. Okay, what's next? We showed that this map is actually well-defined. Now we have to show that it's an isomorphism. That is 1-to-1 and onto. We'll start with showing that iota is 1-to-1 or injective. Recall what this means. If 2 elements in the domain, so an and bn, get mapped to the same place, then they must have been the same to begin with. So how are we going to show that? Well, notice that this first condition here is the last condition of being well-defined. And also, every single one of these arrows can be reversed. And that's all we need to do. So for example, let's just practice. If we start with this condition, iota of an equals iota of bn, well then by definition of iota, that means that phi of a equals phi of b. And we can move this over to the left-hand side and write phi of b inverse, phi of a equals the identity. And now we can use the property of homomorphisms to write phi of b inverse a equals the identity. But that's the same thing as saying b inverse a is in the kernel to begin with. And if b inverse a is in n, then by our boring but useful coset lemma, b inverse a times n equals n. And we can move the b inverse over and just get ab equals n. And that is what we had to show. So notice how there's this duality between being well-defined and being 1-to-1. And that's something that we will examine later in this lecture as well. Next, we have to show that iota is actually a homomorphism, which means that iota of an times bn equals iota of an times iota of bn. Actually, it's probably wise to do this before we prove injectivity, because in some cases, we actually might use a property like this to prove injectivity. But in this case, we didn't. And the reason why I did injectivity first is because it could fit on the bottom of that previous slide, and I could just reverse all the arrows, and I think it's helpful to see that. But for this, how do we do it? Well, like most parts in this and the other isomorphism theorems, you kind of just follow your nose and use the definitions and basic properties. For example, iota of an times bn, well, is just iota of abn, because that's the definition of multiplication of cosets. Now we use the definition of iota. Iota of some coset is phi of its representative. And then we use the property of homomorphisms to write phi of A times phi of B. And then using the definition of iota, we write this as iota of an times iota of bn. And that's exactly what we needed to show. It now remains to check that iota is surjective or onto. And this is almost immediate. Let's take any element in the codomain, which in this case is the image of phi. All we have to do is find an element in the domain, in other words, some coset that gets mapped to it by iota. So let's pick any element in the codomain, phi of A. Well, by definition, iota of an equals phi of A, which means that iota is surjective. It's usually not this easy to show surjectivity. It's usually not hard, but this one is almost trivial. In summary, since this map iota from G mod the kernel to the image is a well-defined homomorphism that is one-to-one and onto, it is an isomorphism. And that proves the fundamental homomorphism theorem. Here's a quick corollary, which is really not much more than just a remark, which is for any homomorphism from G to H, the image is a subgroup of H. Think about why that is. We proved that the image is isomorphic to G mod the kernel, so it is a group, and by definition, it is a subset of the codomain. Let's now look at two extreme cases of the fundamental homomorphism theorem. First of all, if phi is an embedding from G to H, then the kernel is trivial. The fundamental homomorphism theorem says that the image is isomorphic to G mod the trivial subgroup, which is isomorphic to G. In other words, if we have an embedding, then the image, which is a subgroup of H, is isomorphic to G. So we say that G embeds into H. That's the reason why we call it an embedding. On the other hand, if phi is the trivial map from G to H, in other words, every element gets mapped to the identity, then the kernel is all of G. In this case, the fundamental homomorphism theorem says that the trivial group is, which is the image, is G mod the kernel, or G mod G, and of course we know that that's true. Next, I want to use the fundamental homomorphism theorem to determine all homomorphisms between cyclic groups. We'll start with C₄ to C₄. Now we can't always do this for general groups, but I'll show you some examples where we can say something. First of all, you should look at this and say, there's not going to be any other than the trivial one, because this is a 4 cycle and we're somehow wrapping it around a 3 cycle, and there's really no way to do that. But let's prove it. By the fundamental homomorphism theorem, G mod the kernel is isomorphic to the image, which is a subgroup of C₄, which means that the image must have size 1 or 3. However, the kernel is also a subgroup of C₄, so by Lagrange's theorem, its order must be 1, 2, or 4. Therefore, the size of the image, which we know is 1 or 3, must be the size of G mod the kernel, which has to be a divisor of 4, so 1, 2, or 4. And there's only one possibility. It has to be 1. Since the image has order 1, the only homomorphism is the trivial one. Let's do a more complicated example. Find all homomorphisms from Z4 to Z16. By the Fundamental Homomorphism Theorem, Z44 mod the kernel is isomorphic to the image, which is a subgroup of Z16. This means that 44 divided by the size of the kernel must be a divisor of 16, so 1, 2, 4, 8, or 16, but it also must be a divisor of 44. So that's why I've crossed out 8 and 16. Since the kernel must divide 44, the only three cases of the size of the kernel are 44, 22, or 11. That's 44 divided by 1, 44 divided by 2, and 44 divided by 4. Now, a quick reminder, for each divisor D of n, the cyclic group Zn has a unique subgroup of order D, which is generated by n over D. If you're a little rusty in this, I think by the time we finish this example, it'll come right back. Let's consider these cases one by one. In the first case, when the kernel has order 44, that forces the image to have order 1. Do you remember why that is? It's due to the Fundamental Homomorphism Theorem, and also, I guess, Lagrange's theorem. Because it says that G mod the kernel, let's write this down here, G mod the kernel is isomorphic to the image. In other words, the image is isomorphic to a collection of cosets, and the number of cosets is the size of the image, and then the size of each coset is the size of n, which is the size of the kernel of phi. So G is partitioned by this many cosets of size this. So size of the kernel times the size of the image has to be the size of the group. So in this case, the image has size 1, which means that the image is the trivial group in Z16. So the homomorphism must be trivial. It sends every element to 0, and in particular, the generator. In the second case, the order of the kernel is 22, so the order of the image is 2. There's only one subgroup of Z16 of order 2, which contains 0 and 8. That's why I put this reminder up here. Zn has a unique subgroup of each order, or for each order that divides the size of the group. So if this homomorphism is not to be trivial, it must send the generator 1 to 8. And then it follows that phi of 2 equals phi of 1 plus phi of 1, which is 8 plus 8, which is 0. And similarly, phi of k is going to be 8 if k is odd, and 0 if k is even, defined on Z44. Finally, consider the case when the kernel has order 11. This means that the image has to have order 4, and there's a unique subgroup of order 4 in Z16, which consists of the elements 0, 4, 8, and 12. So if you think about a Cayley graph of that, 0, 4, 8, 12, well, we can take 4 to be a generator, or we can take 12 to be a generator. So in other words, this is generated by 4 or by 12. So there are actually two homomorphisms from Z44 to Z16 in this case. One of them sends 1 to 4, and the other one sends 1 to 12. And if you want, I'll let you work out what the other elements get sent to, and it just depends on what they're equivalent to mod 4. Let's now return, as promised, to the concept of well-defined, which we saw in the proof of the Fundamental Homomorphism Theorem. Back in Chapter 3, we encountered this term when we were claiming that a binary operation on a set of cosets was well-defined. And in this video, we saw it applied to a function defined from a group of cosets. In both of these cases, well-defined meant that our definition, either of a binary operation or of a function, does not depend on our choice of coset representative. Formally, if n is a normal subgroup of G, then an times bn equaling abn is a well-defined binary operation on the set of cosets because this definition does not depend on our choice of representative. In particular, if a1n equals a2n and b1n equals b2n, then a1b1n equals a2b2n. In other words, if I choose to call this coset a1n and b1n, and you choose to call it a2n and b2n, and we both use this definition, we're going to get the same answer. Earlier in this video, we proved that the map iota, defined in cosets, where iota of an equals phi of a, was well defined because that also did not depend on the particular choice of representative a. In other words, if I call a coset an and you call it bn, then we better get the same answer. So iota of an has to be equal to iota of bn. And we proved this. We showed that phi of a will equal phi of b, and that's how it was defined. In general, whenever we define a map and the domain is a quotient, we must show that our definition is actually well defined. In some sense, well defined and injective are dual concepts. In particular, if f is well defined, then the same input cannot map to different outputs. And that's given by this picture right here. So if we have two different names for the same element, then of course, if this is a function, they can't get mapped to different things. So this little motif is not allowed. If f is injective, it's going to be given by this whole diagram, then different inputs cannot map to the same output. In other words, if an and bn are different, then you can't have two arrows going into the same input in the codomain. And even though we did it a few slides ago, let's revisit the proof of the Fundamental Homomorphism Theorem, where we defined iota. And showing iota is well defined is done as follows. We suppose that we have two cosets that are the same, so like we did right here. And then we said, well, we can move the b over to the left-hand side. We can use our boring but useful coset lemma to say that b inverse a is in n. And since n is the kernel, that means b inverse a get mapped to 1, the identity. And then using the property of homomorphisms, we can write that as phi of a equals phi of b, which means that the maps were the same to begin with. And then, like we did in the proof of the Fundamental Homomorphism Theorem, we just reverse the arrows to get that iota is 1 to 1. Now, several comments. First of all, there are plenty of homomorphisms that are not injective that we will encounter as early as the next lecture, for example, on the later isomorphism theorems. So for these, you cannot just reverse arrows and conclude that they are injective because they are not. And secondly, I feel like a lot of proofs where you have to show well-definedness and injectivity, you can just reverse arrows like this, but probably not every one of them. I can't think of any off the top of my head, but there are probably some that are more delicate or complicated where it takes a little bit more than just this. But I think it's worth seeing this duality and kind of understanding how these concepts are related. The standard way to show that two groups are isomorphic is to construct an isomorphism between them. However, if the domain G is a quotient, then there is another method due to the fundamental homomorphism theorem. Suppose we want to show that G mod n is isomorphic to H. There are two things we can do. First, we can define a map between the two groups and prove that it is well defined because the domain is a set of cosets, a homomorphism, and a bijection, one-to-one and onto, just like what we did for the fundamental homomorphism theorem. But now that we have that theorem in our arsenal, we can just apply it and define a map from G to H, prove that it's a homomorphism, a surjection, that is onto, and that the kernel is equal to n. So this is one fewer steps than that one because a bijection, you got to show one-to-one and onto. So it's a little bit easier. As well-definedness sometimes can be tricky. In general, I think method 2 is typically easier, but you can often do either one. Also, sometimes, like in the next lecture, we will define a homomorphism between a quotient of a quotient. In that case, it's really not easy to talk about cosets of cosets. Let's briefly discuss several examples of where this method is useful. First, it can be used to show that the quotient of the integers by the multiples of n is isomorphic to the cyclic group Zn. I'll hold off on saying more about this because I'll show you a picture on the next slide. The second example is the quotient of the non-negative rational numbers, Q star, by the subgroup generated by -1 is isomorphic to the positive rational numbers. Now, I do want to say a bit about this. So first of all, these are multiplicative groups. So the subgroup generated by 1 is just plus or minus 1. Notice that if we were looking at the additive subgroup of the rationals, then the subgroup generated by -1 would be all -1, -2, -3, and the negatives, which are positives. It would be an infinite subgroup, the integers. But for here, to prove this isomorphism, we can define a map phi from the non-zero rationals to the positive rationals. And now how would we do that? Let's take a rational number and let's call it a. And which positive rational do we send it to? Well, what about the absolute value of a? What else would we do? So why is this a homomorphism? Well, phi of a times b is the absolute value of ab, which is the absolute value of a times the absolute value of b, which is phi of a. It almost falls right out. That is a homomorphism. So that worked. Why is this onto? Well, of course, every non-zero or every positive rational number has two preimages. So this is how we show it's a homomorphism. What about onto? Well, take any a in positive rational. Well, phi of a equals a. And then the kernel, what are the things that get mapped to the identity? Well, what is the identity over here? I'm not going to write this one down. I'll just say it. What's the identity over here? Well, it's 1. So what gets mapped to 1 under here? It's 1 and -1. And so this follows immediately from this technique using the fundamental homomorphism theorem. The next two things, well, this is our fourth isomorphism theorem that we will see, called the diamond theorem. And we'll see that in, I think, 2 lectures from now. And this last one, I don't want to say too much about because I usually leave it as homework. It's a great exercise, but it is in some sense, the group theoretic analog of a classic result from ring theory called the Chinese or Sun-Si remainder theorem that we will see in either Chapter 8 or Chapter 9. I forget which one. But again, I encourage you to try this. You start by defining a map from A to G mod A cross G mod B. Now, how do you think you define that map? Well, let's take an element little g, and you got to send it to a pair of cosets. So there's not much you can do. What about GA, comma GB? And you have to show this is a homomorphism. The kernel is A intersect B, and think about when is this element the identity pair of cosets? Well, that's when G is in A and in B. But then you have to show that this is onto, and that is actually, surprisingly, the non-trivial part of this, and you need the fact that G can be written as a product of something in A times something in B. Okay, so I encourage you to try that out. As promised, here is a picture of the fundamental homomorphism theorem being used to show that the integers mod 12z, that is the multiples of 12, is isomorphic to z12. So if we have a homomorphism from z to z12 defined by sending k to k mod 12, then the kernel of that homomorphism are the multiples of 12. And if we quotient out by that kernel, we get this picture here. And this has the same structure as Z12 via this relabeling isomorphism. I don't know about you, but I really like this picture. And it really just says that this is what homomorphisms look like, even for abstract, complicated groups that aren't just the integers. I want to finish this lecture with a familiar example of a homomorphism that is neither an embedding nor a quotient. Recall that we saw this in the previous lecture, so I hope you watch these in order. This is from the quaternions to the alternating group, and it's defined on the generators I and j by sending I and j to two elements of order 2, and then k has to get sent to the other element of order 2. And it's easy to check that -1 gets sent to the identity, and negative I, j, and k gets sent to the same thing as I, j, and k. So the kernel of this is just a subgroup generated by -1, and here are the cosets. And notice that this picture, G mod the kernel is isomorphic to the image. And this isn't really much different from the example that we did earlier, just that the image is sitting inside a larger group, a larger universe. The moral is that every homomorphism, phi from G to H, can be factored as first a quotient by the kernel and then an embedding. So here are those maps between the groups, and here's the individual elements. So G gets mapped to the coset that contains it over here, and then we send that to phi of G here. The only difference between this and the fundamental homomorphism theorem is that we are not just looking at the image. We're saying, well, the image of this might live in a larger universe. So G mod the kernel is isomorphic to the image, but that might live in somewhere bigger. And the proof of this is just like the proof of the fundamental homomorphism theorem, but you just drop the condition that this map iota has to be onto, because the map iota is onto its image, but the image does not have to be all of H. So it's basically an immediate consequence of the fundamental homomorphism theorem. And here is a picture of that very homomorphism in this familiar diagram, where we see that phi can be decomposed into first a quotient by the kernel, and then an isomorphism that relabels the cosets to the elements in the image, which may or may not sit in a larger subgroup H. So that is a good place to stop. And to think about what's coming next, well, if I were to summarize the content of this lecture in a single sentence, it would be every homomorphic image is a quotient. So the next natural thing to ask is, okay, what can we say about the structure of a quotient? What are its subgroups? Which ones are normal? And what happens when we take the quotient by one of those normal subgroups? In other words, what's the quotient of a quotient? And that is what the next two isomorphism theorems, the correspondence and the fraction theorem, are all about. And that's the topic of the next lecture. In it, I'll show you a number of creative visuals that are unique to my book and video series that I think really provide intuition about what these theorems are all about and why they are what they are. I think you'll really enjoy it, so don't go anywhere.